We want to continue our discussion on functions, and as I mentioned at the end of the first video, there are numerous ways to represent a function. There are actually 5 different ways within the realm of functions that they can be represented. They can be represented verbally, using words, numerically, using a table, diagrammatic, using a picture or a diagram, graphical, and then symbolic. And so we're going to look at each one of these representations and think about the pros and cons, when you would want to use which one. And as we go throughout these representations, we're going to use an example. And the example that I want us to use as we go throughout this discussion is the square of a number x. Okay, so as we go throughout this particular discussion, this is the focus. This is the example that we're going to be looking at each time. Okay, is an example. The example will be the square of a number x. So first off, let's talk about verbal. With verbal, we use words to describe what is being computed. Think about it like almost like a recipe or like an algorithm within a computer program. It's a step-by-step process. You're telling someone what to do in order to find, in this case, the square of a number. It can be given orally by reading it, stating it, or it can be written. And again, it can also be written in that algorithmic form where you're doing it step by step. So for example, using our example of a squaring a number, we could just write a good old everyday sentence to calculate the square of a number. So I tell you what I'm going to do, and then I tell you how to do it. Multiply x by x to obtain y. Okay, so you can just write a complete sentence. Again, you tell me what you're doing and how you're going to do it. To calculate the square of a number x, multiply x by x to obtain y. Or you might see it written in something simple. This is almost like writing a computer program where it says input a number x, multiply x by x, and call this result y, and then output y, which is the square of a number. Okay, that's just a real basic like computer program or algorithm that you can use. Now, one of the benefits of the verbal representation that's not listed here on the screen is that with a verbal representation, I can actually perform the calculations or perform the operations for any value of x that I could possibly think of, because all I have to do is follow the guidelines. So whether I choose x to be a positive number, a negative number, a fraction, a decimal, as long as I follow the instructions of multiplying x by x, I'm going to obtain y, which is the square of a number. So that's the benefit of using the verbal representation, is that you can apply it to any number that you can think of. The second representation is numerical, which is a fancy way to say a table of values. And it provides you a list of input and output pairs. You can write it as a list of ordered pairs, such as you see right here. Okay, so you can see it written as a list of ordered pairs like you see right here. The input is 1, the square of 1 is 1. Input is 2, square of 2 is 4. Input is 3, square of 3 is 9, and so forth. You can also write it in a table form, which is probably the form you're used to seeing. So if you have a table, we usually have the x value, or our input is on the left, and our output is on the right. And I don't have to use the same number, so I might use -2, -1, 0, 1, and 2. And I would have -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So there's a table which represents the input and output. But the challenge is with the numerical representation, all I know is the value for -2, -1, 0, 1, or 2, or I know in the list of ordered pairs, I would know the value for 1, 2, 3, 4, 5. Okay, so you're limited on the information that you get, and it's explicit. What I mean by the fact that it's explicit is that really there's no calculations involved because you're given the ordered pairs or you're given the table, so that basically what you see is what you get, or what you see is what you know. You don't know anything else. And so it's virtually impossible to list all the possibilities because our number system is infinite. So the table is a good one if you're trying just to look at certain values or specific values to use. Otherwise, you may want to use a different representation. Third is diagrammatic. With diagrammatic, they're using a diagram or a picture that doesn't necessarily involve words or formulas or tables. For example, you might have a diagram that looks something like this. You could have like an oval to represent your input. So we might have -2, -1, 0, 1, and 2 again. And then you have a second oval to represent the output. And then we use arrows or connectors to show -2 would be 4, -1 is 1, 0 is 0, 1 is 1, and 2 is 4. So you get to see the relationship visually. And typically in the diagrams, again, like the table, your input is on the left and your output is on the right. So again, you're limited to what you see or what's given. There's no calculations involved, but it's also, again, difficult to list every possible input and output combination. And so the diagram is sometimes not the best option either. Fourth, is the graphical representation. The graphical representation was first introduced by a mathematician who was named Leonard Euler. He also invented the function notation that we talked about earlier. And again, it actually visually compares or pairs your X and Y values, and we actually would show them plotted on our good old everyday grid system where you have the horizontal number line, which represents your X or your input, and the vertical represents your Y or your output. So, for example, so we would actually show them visually paired. So, for example, we had 0, 0. We had 1, 1. 2 squared is 4, so you would have 2, 4. So you get to see it visually on the graph, and there's not really a lot of calculations. So again, it's explicit because you're simply reading the information from the graph. Now, the benefit, though, one of the benefits of the graph is you get a little bit more information, you get more complete information for a given interval, because I could actually kind of get an idea. I could estimate what the value would be, say, if I were at 1/2. Or I could estimate what the value might be at, say, 1 3/4. Okay, because I could visually inspect my graph and get a sense. So I get a little bit more information, but it requires estimation. So sometimes we might be a little bit off as opposed to actually doing numerical calculations. And finally, the last one, the symbolical, is where you actually have the formula. You basically take the verbal, the words that you have, and you convert it to the mathematical symbol. So we have it written in kind of the shorthand notation, where you write it as an equation using x's and y's and equals and operation symbols and so forth. Again, the benefit of the symbolic is if you have that formula and you basically plug and chug into the formula, then you can find the value for any x that you could possibly think of. So ideally, you'd love to have verbal or symbolic because it works for anything. But again, depending upon the scenario, one of the other representations might be a good one. So a lot of times we get the question, well, which representation is best? Well, that kind of depends on the question that you need to answer, what information you're trying to share, and who you're trying to share it with. Most newspapers, magazines, and TV reports are going to use tables and graphs because with tables and graphs, you can very easily communicate a lot of information in a quick way. They're easy to read. People can kind of tell very easily whether something's increasing or decreasing. But if you read scientific journals or research journals, they're going to be actually more precise and more accurate. So they're going to probably use verbal or symbolic. Now, they may include some graphs and tables to go with it to make their report interesting, but they're also somewhere going to, in the body of their report, going to have the verbal or the symbolic representation, or even both. Okay, so a couple of things we know. We know that every function is a relation, but not every relation is a function. You want to see that in a visual, think about it this way. If you picture a big circle as a relation, and a relation simply means two things are related somehow. Within the relation, there's a smaller subset of items that we call functions. And the functions have that special characteristic that for every valid input, there is exactly one output. And so as you begin looking at these problems, that one of the first questions you have to decide is, does your relation represent a function? And ultimately, you're either going to say, yes, it does, or no, it doesn't. Now, why do you want to do that? Well, if we're able to determine that we have a function, that's a stronger statement, and that guarantees a unique output for each input. Also, though, once you identify that it's a function, you want to also be able to identify the domain and the range. Remember, domain is your x values or your input, and your range is the y values or your output. And so it gets kind of tricky because you don't know whether you're going to have a table or a graph or a diagram or an equation. So I want us to take a look at how to do that for the different representations. How to determine, first of all, is it a function? And if it is, state the domain and the range. Okay? So first of all, basically, if you're given a numerical model, which is a table or a diagram, it's a visual inspection. You're going to look at your graph, look at your table, look at your diagram, and basically ask yourself, is each x value paired with exactly one y value? And if you say yes, then you're going to say, yes, it is a function. If you say no, then you're going to say, no, it's not a function. And as I've already mentioned, typically in a diagram and in a table, the left-hand column is your inputs, which is your x and would represent your domain. The range is the right-hand column or the right oval, and it would represent the output or the y's. And we're going to take a look at some examples in just a few minutes at the end of this video, so hang on. Oh, here's some examples already. So that's fine. We can go ahead and do those. Okay, so if we look at this first one, we have a diagram, and it shows that -2 pairs with 1. It also pairs with 3. 0 pairs with -3. 1 with 4, and 3 with 1. Okay, so I'm going to ask myself, is each x, what was the question? Let's make sure I get the question right. Is each x value paired with exactly one y? And so when I'm looking at this equation, I'm going to have to say no, okay? Each x is not paired with exactly one y because -2 is actually paired with two different values. So I would have to say no, each x is not paired with exactly one y. So this is not a function. This diagram does not represent a function. All right, then looking at the second diagram in the lower left corner, in the right-hand circle or oval, you have 1, 2, 3. 1 is paired with 1, 2 is paired with 4, and 3 is paired with 9. So then I ask myself, is each x on the left paired with one y on the right? And the answer is yes. So I know that this example is a function, or this relation is a function. So since it's a function, I want to identify the domain and the range. Remember, the domain is your inputs, and it's just a list of numbers. So I'm going to put a little brace, okay, the little squiggly line, and I would list them 1, 2, 3. We generally list them low to high, okay, and separate them by commas. The range would be the values on the left or in the left oval. And again, it's just a list. So I'll put my brace. I have 1, 4, and 9. And again, we normally put those in order from low to high. All right, then looking at the table, the first table in the upper right corner, you have -2 paired with 2, -1 with 1, 0 with 0, 1 with 1, and 2 with 2. Okay, so you got to ask yourself, is each x paired with exactly one y? The other thing to think about, is there any repetition in the x values? And in this case, there's no repetition. Now, some of you may want to say, but look, you have an output of 2. It's okay for the output to repeat, okay? It's the input that cannot repeat. So this particular one, in this upper right-hand corner, we would say, yes, this is a function because each x is paired with exactly one y. And again, if we start thinking about stating our domain in the range, remember the domain is your x, so that's going to be the column on the left. And so I would have -2, -1, 0, 1, and 2. My range is the y values. And notice when I write this list, even if the value repeats, I don't repeat it. So I'd have 0, 1, and 2. Once it's in the list, it's in the list. There's no need to repeat it. All right, looking at the example in the lower left, it looks like it's matching colors to pets. So we have orange cat, blue dog, orange fish, green gerbil, yellow rat, red snake. Okay, so I want to ask myself, is each x paired with exactly one y? And I have to say no, because I have an orange cat as well as an orange fish. So the color orange is paired with two different pets. So because of that, we have to say no, this is not a function. Okay, moving on. Here's an example where you have ordered pairs, okay, instead of tables. With ordered pairs, again, you want to look at it, and I can look at all my inputs. So I have -2. Let's see what I've got. I've got -2 paired with 5, -1 with 0, 0 with -3, 1 with -4, 2 with -3, 3 with 0, and 4 with 5. So if I'm looking at that again, thinking about is each x paired with exactly one y, I basically am looking for any repeat in the x values. There is no repeat, so I would say, yes, this is a function. Okay, then identify the domain and the range. Again, the domain is simply a list of your inputs, okay, and we just make the list. -2, -1, 0, 1, 2, 3, and 4. The range is the list of outputs. So let's see, we have in order from low to high, -4, -3, 0, and 5. Now again, notice there are a few of those y values that repeat, but it's okay for the y value to repeat in terms of it being a function. All right, then looking at the next one, we have -1 paired with 6, 2 with -4, 3 with 8, 3 with -12, and 5 with 1. So in this scenario, I notice that I have the 3 occur twice and it's paired with different numbers. So I would have to say, no, this is not a function. Okay, now, if you're given a graphical, let me put the word graphical in here, looks like it got erased for some reason, graphical, so that you have one of those that's on the grid system. We have a special test called the vertical line test, okay, that we use to decide whether or not it's a function, okay? So we use the vertical line test, and I usually will abbreviate V for vertical, L for line, and T for test, so I don't have to write that word out every single time. But what you do is you visualize, you can even hold your pencil up vertically, which is up and down, okay, and imagine it running it across the graph and thinking, do I cross that graph at more than one point? You can cross it one time, and that's acceptable. If you cross more than one time, then it's not acceptable. Finding the domain and the range is a little bit trickier, okay, because you got to think about what's going on beyond the edges of your paper. So it's important to notice when you're looking at the graphs whether or not they have arrows on the end, which indicates it keeps going on forever and ever in that particular direction, or does it have like a dot where it stops, and so forth. Typically, to state the domain and the range for a graphical representation, we do actually use interval notation, which I know some of you had found challenging in the previous lessons. So let's take a look at this example. This example is, and we're focusing on, what you want to focus on is this red line. And I'm going to go ahead and I'm going to highlight it a little bit better where you can see it if I can keep straight here. Sorry, that's a little crooked. Okay, so we're focusing on that line. Now, this was a computer-generated graph, so we have to assume that there are arrows on the end. Okay, so I'm going to visualize vertically, hold my pencil vertically, and I'm going to kind of draw some in here so you can see it. But visualize vertical lines. Okay, imagine this is your pencil, and you're visualizing these vertical lines. Any of those vertical lines, no matter where I draw it, it only crosses the graph one time. And one time is acceptable. So we would have to say, yes, this is a function, and it's a function because it passes the vertical line test. Now, again, it's a little bit more involved to find the domain and the range. Remember, the domain are the x's. So it's kind of like you want to imagine you're a little person standing over here, and you're way over here at like negative a million. Okay? And you want to think about, if you were to look up or down when you're standing there, are you going to actually see that red line? Now remember, that red line's got arrows on the end, and it's going to keep going forever and ever and ever and ever in both directions. So, yeah, I think I would see it if I were standing at negative a million. And so then I start walking. Okay, we start walking till we get to the other side. We're going to get over here to the other side, and I'm at positive a million. And again, I want to think about, if I'm looking up and looking down, am I going to see that graph? It's a line, guys. From a geometry perspective, a line goes on forever and ever in both directions, which means I'm going to see it every time, all the time. So our domain is actually all real numbers. Any number that we can see here, whatever, on the number line. In interval notation, remember, that's from negative infinity to positive infinity. Then we also have to think about the range. Now, the range to me is sort of like riding an elevator, because in the range, you'd be way down here, sub-level at negative million on the y, on the vertical, okay? And you're getting on the elevator, and you're going to look left and right, and you're going to ask yourself, would I see that graph? Okay, and then you start moving up the elevator, okay, till you get to the top, and you're at 1 million up here. And again, you're looking left and right and thinking about whether you're going to see the graph. And again, because it's a line and it goes on forever and ever in both directions, we are going to see it. So again, it's all real numbers, or negative infinity to positive infinity. Okay, so it takes a little bit more effort to think about whether or not it's a function. Okay, here's another one. Okay, this one's a curve, and I'm going to draw the curve in. Again, I'll make it a little bit darker where you can see it. Hopefully I can draw it without too much issue. Okay, and again, it's computer generated, and so we have to assume that it does keep going forever and ever in both directions. So the first thing we do is we begin imagining vertical lines on our graph. Okay, you want to make sure that anywhere you draw a vertical line, that it only crosses the graph one time. Okay, and it appears that regardless of where I draw that line, it does only cross one time. So we would say, yes, this is a function. Okay, then to think about the domain and the range, typically, notice how this one, because you have those arrows on each end, as it's going up or down, it's also moving outward horizontally on the left and right. So typically when you have arrows on both ends, a lot of the times, unless you have a definite beginning or ending point, the domain and the range, again, think about being over here at negative a million, and walking along, and I'm going to see it. So my domain would be negative infinity to positive infinity, are all real numbers, and the range would also be negative infinity to positive infinity. Okay? All right, looking at this one, you got the blue circle. So if you think about drawing the lines, notice when I draw a vertical line at this particular point, I cross 1, 2 times. If I draw a vertical line over here on the right-hand side, I cross 1, 2 times. More than one is bad. So we would have to say, no, this is not a function. If it's not a function, I'm typically not even going to consider what is the domain and the range? Okay. All right, let's think about symbolic. And again, looks like my word got off. So the symbolic representation, the best way to do it is to use your graphing calculator to create a picture of that function and then use the vertical line test. And you could also then use the graph to determine the domain and the range. But a couple of things from an algebra perspective when you're thinking about domain and range is pretty much the domain for a symbolic representation is going to be all real numbers with two exceptions or two restrictions. If it is a fraction, then you have to worry about a 0 in the denominator. Or if you have a square root or an even indexed root, like that would be something like square root or fourth root. Okay, so this would be something like square root, fourth root, sixth root. The division by 0 would be like having a fraction, and you don't want to have 0 in the denominator. And when you have these even indexed roots like square root, fourth root, sixth root, you got to make sure that the number underneath is not a negative number. Because if it's negative, then that gets us into dealing with imaginary numbers or those I numbers. And so we don't want to have to deal with those. So we avoid those numbers as well. Okay, so let's look at a couple of examples. I don't have my graphing calculator pulled up, so I'll try to do these for you by hand. So looking at f of x squared minus 1, okay, I'm going to come over here and do a rough sketch of it. It doesn't have to be perfect because you just need to get a basic idea of what the graph is going to look like. I recognize that it's going to be a quadratic. Okay, so I can plug that into my graphing calculator and I would get something that looks like this. Okay, it's kind of that U-shaped curve. And so if I visualize the vertical lines, then I can see that a vertical line only crosses one time at any given point. So I could say, yes, this is a function. Okay, and I noticed that it doesn't have any kind of a special thing. It's not a fraction, doesn't have a radical, so my domain would be all real numbers. For the second one, okay, again, if I think about drawing it, I'm going to draw it over here to the side underneath this one. Okay, so I have positive 3. Okay, so I'm going to have this line. Okay, for the second one, for 2x plus 3. And so again, if I think about a vertical line is only going to cross at one time. So again, I can say, yes, this is a function. Sorry, left out a word there. Okay, and again, my domain, there's no restrictions because I don't have a fraction and I don't have a radical. So I have a domain of negative infinity to positive infinity. So then if we move to the third one where you have x plus 1 divided by 2 minus x, that's kind of a funky looking graph, okay? So let me see if I can draw it for you. All right, I'm going to draw it kind of over here on the other corner. right here. Okay, here we go. Oops, let me get my blue. All right. I would have a curve that does something like this, and then a curve that does something like that. Okay, something along those lines. It's probably what your curve's going to look like. But again, as you're looking at it, hopefully you can see that it does pass the vertical line test. Okay, because the vertical lines are going to cross it. So yes, it does represent a function, but I noticed that that one looks like a fraction. So I have to be careful as I think about the domain. In fact, some calculators, it'll look kind of funky, but right in the middle of this graph, it may look like on your graphing calculator that there's this big old line here at 2. That's because you have a restriction. See, you got to make sure this denominator, 2 minus x, it cannot be 0. And so if I solve that for x, I find that in this particular equation, I cannot use a value of positive 2, because if I do, that causes the denominator to be 0, and that's a big no-no in mathematics. So you have to be aware of that, and your graphing calculator knows that, but it's not smart enough to leave out that crazy line. So yes, it is a function, and our domain is going to be any number that we want to use except 2. So in interval notation, you write from negative infinity to 2, or 2 to infinity. You can do either side of that 2, but you can't use the value of exactly 2. And then one more. Let me see if I can squeeze this one in. I'm going to do it off over here to the side. Okay, so we're going to create the graph. I don't think I went out far enough. I got to go to 7, I believe. Okay, so I would have, whoops, let me get my blue. Be at 7. And it's going to do something like this. Okay, so again, it does pass the vertical line test. Okay, it does pass the vertical line test, but I have to guarantee that this expression underneath is positive. Now, the way we say that, mathematically, the way we say that it's positive is we say that 7 minus x is greater than or equal to 0. So if I solve for x by subtracting 7 from either side, I have negative x greater than or equal to negative 7. You just did this in some of the earlier lessons. We divide by negative 1, so x is less than or equal to positive 7. So in interval notation, that's basically saying I can use any number that's less than or equal to 7. So in interval notation, that tells me that my domain goes from negative infinity to positive 7, and it can be used, so we use a bracket. Okay, I know this is a lengthy video. I've gone through a lot of it fast, okay, but hopefully through this resources and the others, you can get a grasp of functions and identifying domain and range.